Hello everyone, and welcome to this extended deep dive into one of the most captivating and, at times, mind-bending areas of modern physics, time crystals. I'm Ollie, a physicist who loves blending hard science, philosophy, and those profound what-if moments. Today, we're going to dissect time crystals on a more advanced level, not just to grasp the basic principles, but to delve deeper into the theoretical frameworks, emerging research, and the philosophical undercurrents that challenge our notions of time, symmetry, and reality itself. Let's begin with the core concept. A spatial crystal, like salt or a diamond, derives its special properties from a spontaneous breaking of translational symmetry in space, where atoms line up in a regular lattice. Time crystals replicate this idea in the temporal dimension. Specifically, we're looking at a system in its ground state, its lowest energy configuration, that exhibits periodic motion or oscillations in time. This spontaneous breaking of time translational symmetry was once considered impossible under equilibrium physics, as perpetual oscillations at zero net energy cost suggest a perpetual motion machine. Yet, time crystals circumvent such thermodynamic paradoxes through phenomena like many-body localization, MBL, which traps energy in localized regions, inhibiting the system from uncontrolled heating. To stabilize this periodic behavior, experimental setups often involve Floquet engineering, applying external time-periodic driving, such as laser pulses or microwave fields. The system locks in to a subharmonic response, oscillating at a frequency that's a fraction of the driving frequency. This subharmonic locking is crucial. It confirms that the system has found a stable time periodic state, distinct from trivial thermal behavior. It's almost like the system is ticking in sync with its own internal rhythm, even though the external drive has a higher frequency. Now, why doesn't this break the laws of thermodynamics? Here's the subtlety. Time crystals aren't generating energy. Instead, they are evading thermalization. MBL acts as a kind of shield against the usual chaos that leads systems to heat up. Because of the disorder or specific interactions in the system, the energy can't flow freely, and the crystal's oscillatory state endures. It's conceptually similar to those neat illusions in classical physics, a whirlpool that sustains its shape without external energy input. But in the quantum realm, we have a rigorous explanation rooted in many-body quantum mechanics and the possibility of a localized phase that prevents ergodic behavior. When Nobel laureate Frank Wilczek first proposed the idea of a time crystal in 2012, it seemed almost like science fiction, challenging foundational concepts of equilibrium physics. Yet by 2017, experimental demonstrations emerged from labs at MIT, Stanford, and Harvard, largely using trapped ions and ultra-cold atoms as test beds. Subsequent studies explored more intricate settings, spin systems, superconducting qubits, and even condensed matter platforms like yttrium iron garnet, YIG spheres, where magnon modes can mimic time crystalline order. Each of these platforms offers a slightly different insight into how discrete time translational symmetry might be broken and how stable these oscillations can be under real-world conditions. Philosophical provocations, Nietzsche versus Bergson. Now, let's turn to the philosophical dimension. Friedrich Nietzsche's concept of eternal recurrence posits a universe perpetually cycling through the same events. Time crystals aren't literally recreating Nietzsche's cosmology, but they raise the tantalizing possibility of cyclical structures embedded in quantum reality. Are we glimpsing the faint outlines of a universe where time loops back on itself in certain microscopic contexts, defying our conventional arrow of time? On the other hand, Henri Bergson distinguished between chronos, clock time, and durée, the flow of lived experience. In bridging these ideas, time crystals exist within a highly controlled, measurable quantum framework, chronos, but they also evoke the qualitative sensation of a rhythmic flow, durée. This invites us to reflect on whether we're brushing against a hidden architecture of time itself, one that transcends the strictly linear progression we're used to measuring in our everyday lives. Could time be emergent? This question is a favorite among theoretical physicists. Is time a fundamental parameter, or is it something that surfaces from deeper quantum phenomena? Think about how temperature emerges from the collective motion of particles. In an analogous way, maybe our perception of time's arrow arises from aggregated quantum states oscillating in unison. If time crystals point to a deeper mechanism underlying temporal progression, we might have to revise long-standing assumptions about the building blocks of reality. Practical implications. The quantum revolution. Now let's pivot to practical implications, particularly in quantum computing. Qubits are notoriously fragile, prone to decoherence from environmental noise, temperature fluctuations, and electromagnetic interference. If we can harness a time crystalline phase, where qubits remain locked in robust oscillatory states, it could stabilize quantum information, prolong coherence times, and reduce error rates. This approach might leverage the subharmonic synchronization of time crystal modes to keep qubits on the same clock, improving entanglement fidelity across larger arrays. Further down the line, some theorists speculate that time crystals might facilitate new forms of quantum communication. Imagine beaming entangled states across distant qubits, synchronized by a subharmonic drive. This is still speculative, but if it works, it could redefine our approach to quantum networks and distributed quantum computing. It's reminiscent of how superconductors enabled the leap to powerful magnets and quantum devices. Time crystals might similarly accelerate quantum tech by introducing an entirely new phase of matter optimized for coherence. The controversies. Scaling and limits. Here's where the conversation gets a bit more nuanced. While discrete time crystals have been observed in carefully isolated lab conditions, questions remain about scalability. As we try to incorporate more qubits, or move toward less ideal environments, we might encounter difficulties maintaining the delicate balance needed to avoid thermalization. Disorder in the system is both a friend, it supports many-body localization, and a foe. It can be tough to control precisely. Skeptics argue that time crystals may remain confined to niche experimental setups, similar to how certain exotic phases of matter only exist at millikelvin temperatures in specialized cryostats. Nevertheless, scientific history shows us that breakthroughs often begin in these highly controlled environments. Lasers were once dismissed as academic curiosities. Today, they're central to everything from fiber optic communications to precision surgery. Time crystals may follow a similar trajectory, transitioning from esoteric quantum phenomenon to indispensable tool, if we can navigate the engineering challenges. New phases of matter and the nature of time. In a broader context, time crystals represent just one facet of a growing field focused on non-equilibrium quantum phases. We've seen topological insulators expand our understanding of how electronic states can be protected by topological invariance. Now, time crystals highlight how the temporal dimension itself can exhibit robust structures resistant to conventional thermodynamic decay. This line of research is steadily eroding the classical boundary between space and time, hinting that both might house hidden symmetries yet to be fully explored. Continuous time crystals, for instance, are a hypothetical extension that wouldn't require periodic driving at all. Early attempts to find continuous time crystals in equilibrium states ran into roadblocks, leading to no-go theorems. But driven dissipative systems might circumvent these restrictions. If we do confirm continuous time crystals experimentally, it would push us to radically reconsider the fabric of space-time. Perhaps time, like space, can spontaneously freeze or crystallize under just the right conditions. Reflections on zero-point energy and Casimir. Zooming out, time crystals also fit neatly into the broader quantum tapestry that features zero-point energy. the irreducible quantum fluctuations that persist even in a vacuum, and the Casimir effect, where empty space is alive with virtual particles. These phenomena remind us that our classical idea of emptiness or stillness doesn't really hold up at the quantum level. In parallel, time crystals demonstrate that even in a ground state configuration, dynamical structures can emerge, challenging our long-held assumption that ground states must be devoid of motion. It's another reminder that quantum fields are brimming with possibility, defying the neat categories we inherit from classical physics. The intellectual frontier. For me, the greatest allure of time crystals is how they jolt us out of conventional thinking, not just in physics, but in our philosophical frameworks as well. Each new quantum phase of matter underlines how intricate our universe can be, revealing behaviors that no single equation or ideology can fully encapsulate. Researchers like Kamani, Sacha, and others continue to push the boundaries, proposing theoretical models for prethermal time crystals, quasi-crystalline time structures, and more. It's a flourishing domain that invites creative cross-pollination between condensed matter physics, quantum computing, high-energy theory, and even emergent philosophical queries about the nature of time. A huge thanks to Mac Arthur for suggesting this fascinating topic. Your curiosity fuels this channel. If you have more burning questions or want to explore other cutting-edge ideas, I encourage you to share them in the community section. Your input not only drives our discussions, but also reflects the collective spirit of curiosity that propels scientific discovery. So what's your take? Are time crystals the harbinger of a new revolution in quantum physics? Or will they stay confined to arcane, lab-bound curiosities? Do they crack open a hidden door to the true nature of time? Or are we still just scratching at the surface of these quantum mysteries? Drop your thoughts in the comments, and let's keep the conversation going. And as always, remember, stay curious, stay hyper-focused, and keep pushing the boundaries of what we think we know about symmetry, time, and the deep quantum structures that lie beneath. The journey is just beginning, and I can't wait to see you, quantumly speaking, in the next episode.